Hello and welcome back to this crazy series of videos about my MegaWang 2000 Turbo Edition retro graphics and audio hardware project. So I've just got this nice new, quite a large box from PCBWay. It's not my largest, but it is probably the second largest box. This hopefully is going to be a nice working APU board, the Advanced Processing Unit board. Basically, it is a board which, if you know the Commodore Amiga from the old days, the Commodore Amiga had a blitter and a copper chip. The purpose of the blitter chip was to copy large amounts of memory very quickly and to remove the burden from the CPU. And the job of the copper chip was specifically to run very small, very dedicated programs, if you like, which would wait for raster positions, pixel screen positions actually, roughly, and then set registers with the contents of certain values. This allowed the registers on the graphics hardware specifically to be updated really very quickly. You could do all sorts of other effects as well with the copper chip and with this very simple programming ability. But basically this board combines the two. That's what's called the Advanced Processing Unit. Now let's just get my stand knife. Let's open this box nice and carefully and see what we have inside. So the reason why I made this board was that I want to have, like in old retro 2D hardware, I want to have the ability to precisely time screen updates. Now I could try and rely on the CPU to do this, but to be honest, the 1 MHz 6510 8-bit CPU on the Commodore 64, especially when it goes through the user port interface, is not, the fastest way of doing this. And it's not very good actually, if it could, from the hardware, it's not very good actually waiting for specific values. So this is why I created this board, was to enable me to, say for example, wait for a certain screen position as it's scanning down the screen and drawing stuff, and to change video hardware registers usually to allow me to change, for example, the background color or other color palette entries, or to update sprite registers and so on and so forth. So here we go, digging into this. Okay, we have a bunch of bare boards here which I'm not really that interested in. They're really quite heavy, so let's close this box and get rid of it and have a look at the assembled board. So thank you once again to PCBWay for a very quick turnaround. Even though it was Chinese New Year recently, they still turned this project around really very quickly. I'm always really happy with the way that they communicate with the jobs that they do for me. This time the component shortages have been mostly resolved. I was really surprised that they actually managed to find so many components. Doesn't that look fantastic? This board for the APU, this revision here, which is revision 9.4, as you can probably see, it's a little bit tidier than the previous board. Look at all these lovely chips all in a row down here. If I put it up this way, fantastic, looks very, very neat. The only one that's missing is this U24. Apparently it was difficult to find this U24. Luckily enough, I have a U24 374 on hand. which I'm going to put in shortly. However, you know, it's actually useful because I can use this unpopulated socket here to just do a little bit of a continuity check, just to be on the safe side. I know PCBWay have already done their electrical tests, but I usually try and do my own little continuity tests just to be on the safe side. So here we go, ground down here. Nothing at all. Of course it's going to be charging up the capacitors and stuff like that. I'm kind of expecting that. Of course there's beep, as you do expect. This one's usually the ground, this one's usually here. And I can see here that the meter is showing HV, which is fine, perfectly great. If I check the continuity between plus 5 volts here and plus 5 volts up here, it's all there, it's all good. Okay, so I'm pretty confident in this build anyway from PCBWay. They are very good at supplying me with working parts. What I should do is I should set these dip switches up here. There we go. I've already starred the default options, which is what I'm going to be using for this build. The APU has its own internal memory mapped register setup, which is this. There's no fly wire or anything like that going to a header, usually populated on this edge of the board here. There's no video output headers at all. Of course, the user port interface, which I actually had to fix recently because I discovered that there was a bit of a bug in there. It was actually sending wrong information every 256 to 1024 bytes. That's a different story. I thought it was scale sprites board having a flickering sprites issue, but it wasn't. The scale sprites board was actually working perfectly well. It was the user port interface which was sending the wrong data occasionally, very occasionally. Quite a lengthy process to actually find that. I should have really checked the source data first rather than assuming that the great big sprites board was at fault. It actually fixed the audio issues as well. The audio board was crackling. I didn't know why, and it was because it was receiving corrupt information from the user ports. The sound port memory was wrong. Occasionally it would play a wrong note, etc, etc. Okay, that all looks great. It all looks very neat and tidy. So thank you very much, PCBWay. I'm going to populate this here, and I'm also going to populate, of course, the user port interface in here, which is where it's meant to live. Isn't it fantastic? I can almost read that. My eyesight is not as bad as I thought. It's definitely a 374. You know, I always check before I put these in. Sometimes, you know, like once or twice, you get the wrong one in the tubes. Doesn't happen very often, but it does happen. Snap that out. All the pins look good. That's also perfectly great. We're in the right way. Oops. Pins are lined up. Pins are lined up. We've got capacitor out there with the thumbnail's width. And in it goes. With that. any issues. Okay, now let's populate this one. I need to get it from the other side of the room. One moment, please. And as if by magic, here's the offending board. So, what does this hacky little breadboard on top do? Well, I discovered a very long-standing, undetected bug very recently with this little board here. What was happening was that from the Commodore 64 user form, which comes in via here, the Commodore 64 doesn't have any data setup time when it sets its 8 bits that you have just sent over the user form. What it does have is that it has falling edge right at the time, on the signal right at the time when you write data to the user port, the 8 bits, and there is a 1 megahertz low period, and then there is a rising edge. So there is no data setup time, but the data is held for a long time. This board, stupidly, was trying to latch the data on the falling edge, not the rising edge. In other words, it was trying to latch on the negative edge rather than the positive edge. And the positive edge is, of course, where you have 1 megahertz worth of time to have the data set up actually complete. And depending on the revision of the Commodore 64, some data transitions on those 8 bits were taking in the order of 15 to 20 nanoseconds, which was just enough time for these fast gates here to sometimes, occasionally, if it was in the order of 20 nanoseconds, to latch the wrong value, as the 8 bits of the user port were in transition. So what this does is that it's a very quick and hacky fix, is that it adds a couple of extra AND gates for the falling and rising edge signal, for the data present signal basically, and it adds a certain amount of time, which is enough time in this hack to read the setup data. It's not a proper fix. I need to produce a proper fix board for this user port interface, and I'm thinking that at this point in time I will expand the design of the user port interface to include a whole bunch of extra memory and stuff like that. So I'm going to produce a better board for this, but this hack here suffices at the moment. I just want to test this board here, and this is a good reason why I have this daughter board arrangement here. So I can upgrade the user port interface without needing to upgrade the rest of this huge board. So it's actually cost efficient. So what I'm going to do is that I'm going to do my little trick of raising up these headers here, because it makes it easier to plug in this board, because I can wiggle the pins around a little bit more and it's a little bit more forgiving. It's not the best solution to use these kind of sockets for this kind of work of interboard connectivity where you want to remove the board and plug it back in, but it is what it is. I mean, usually for the backplanes I'm using these lovely connectors here, which are fantastic. I haven't done that. Have I got a smaller one that I don't need to serve off? Let's have a look. What ones have I got? Yes, I do. I've got this 3 one here, which I'm going to plop in here, like so. I have these, this is at least 4, so I'm going to use that for the EBS header. There we go. And do I have another 4 one? Nope, so I'm going to use one which is 5 wide. That's not a problem. So we'll put that in here. We'll plop that in there, like so. There we are. Okay, that's all nicely lined up. This gives me lateral leeway when I'm trying to put all these pins in, so it's just a little bit more comfortable like that. Okay, now I need to just populate this longer one here, like so. In it goes. They are a little bit stiff because these are new sockets, of course. They generate, they generally have quite low resistance and quite good signal propagation properties, I found. Certainly good enough for the kind of thing that I need to use them for. There we go. Doesn't have to be exact, of course. Do I have any ones which are narrower than this? No, I don't. Do I? Yep. You see, what I should really do is that I should have the board. I should choose a nice right-angled connector, which goes up like this and then out like that, and then I can have the daughter board slotting in like this. That would be fantastic, wouldn't it? Change the connector, of course, with the user port interface, but if I'm producing a new user port interface, then that's what I want to do. You see, what happens here is that the user port interface exposes the 24-bit address bus here, plus the 8 bits of the data, of course, and also some read and write signals and the vsync signal and stuff like that. This is the 8 bits of the EDS, and then 16 bits here for the address bus. But what happens here is that the APU can choose whether or not to take over the 24-bit address bus and the 8-bit data bus, and it can choose whether or not it wants to do that and then to intercept read and writes that are coming from the user port interface. And what it means is that the APU can then decide whether or not it wants to send data from the user port, or if it can intercept that and then do fast writes to the rest of the graphics hardware via the real memory interface that's here. Let's get everything lined up. Okay. All of that looks good. Now the fun bit of trying to get this one in. So I'm going to move this over here somewhat. Get some light on the situation as well. This side, it always helps to see when you have more light. This is late in the evening when I'm recording this. It didn't arrive until late in the evening. So unfortunately I cannot rely on natural light. Natural light is the best for this situation, but there we go. There we go. I think that's all the pins likely to go in. I don't feel any pins out this side or this side. No, everything seems fine, so I think I can push it home. And if everything is lined up, it should be able to push in quite easily. And ding ding ding, everything seems to be lined up. Everything seems to be good. There we go. Okay, and there we are. The good thing about these headers is that they have, really quite chunky metalwork, which actually supports quite a lot of weight, as you can see here. Let's move that there. So you can see here I've actually produced a little bit of a hacky interface here. I've bent out one of the pins and I've raised up the pins as well for using a connector. So it actually intercepts the underscore PC line, which is the data write line from the cable, splits it out, goes into here, goes around a couple of AND gates, and then it comes back again, goes back into the board. That's how it's hacked in. So that's the board done. Now it's time to plug it back into the rest of the board and to turn it on and see if it works. Wish me luck.